Today, I am going to speak on the measures of association. This will cover Unit 3 of the correlational designs for the second semester and Unit 2 of multivariate techniques for the fourth semester. If we are to look at the quantitative methods, we can have two broad divisions. On one side, we can have the cause-effect relationship, and on the other hand, we can have association. Association is broadly divided into two types, which is usually labeled as association, that is for nominal level measurement and ordinal level measurement, whereas correlation is confined for scale level measurement, that is measurement at the interval and ratio level. Association exists if the distribution of one variable is related to the distribution of another variable. Measures of association indicate, in quantitative terms, the extent to which a change in the value of one variable is related to a change in the value of another variable. Say, for example, when width increases, does height also increase or decrease? This can be a question. The measures of association give us precise numerical answers to such questions. It is important to remember that all these measures do is detect association and not causation. Now let us look at the levels of measurement. At the first level of measurement, following the works of Stevens typology that was proposed in 1946, we have nominal level, ordinal level measurement, interval level measurement, and ratio level measurement. Stevens typology is much debated upon. However, attempts to have other nomenclature or typology emerge with complexity rather than simplicity. Therefore, the current talk will adhere to Stevens typology, wherein we have the four levels of measurement. The first level of measurement that we have is the nominal level measurement, example of which can be sex or gender, the marital status, and religion. At the second level of measurement, we have the ordinal level measurement, example of which can be the social class, socioeconomic status, and the ranks, that is based on marks obtained in examination. At the third level of measurement, we have the interval, example of which can be temperature, say for example in Celsius, Fahrenheit, or Kelvin. Other such examples can be intelligence test scores, personality assessment scores. At the highest level of measurement, we have the ratio scale, example of which can be number of success on experimental trials, height in feet or centimeter, and the width, say for example in kilogram. The table projected the different levels of measurement with their incremental progress on the measurement property, the mathematical operations that is possible, the advanced operation that is possible, and the central tendency that is applicable. The nominal level is having measurement property for classification or membership only, which basically can be referred to as identification. The mathematical operation that is applicable is simply equal to or not equal to, and the individual cases may be grouped together. So the only possible central tendency is the mode. At the ordinal level, we have comparison or differing levels, that is rank or the ordinary position. So the mathematical operation that is possible is greater than or less than, and we can sort the individual cases based upon the differing level of measurement on the ordinal order. The applicable central tendency is the median. For the interval level, the measurement property assigns differences and affinity. At this stage, we can have plus and minuses. Example of such operation can be yardstick, and the central tendency applicable can be mean and deviation. At the highest level, that is the ratio level measurement, we can have the ratio which can be expressed in terms of magnitude or amount. The mathematical operation that is applicable are plus, minus, divide, and multiply. Hence, we can have ratio of, say for example, score on variable x divided by scores on variable y. The central tendency applicable are geometric mean and the coefficient of variation. As we look at the incremental progress of the different levels of measurement, as we move from, say for example, nominal to ordinal, or from ordinal to interval, and so on, we can see that each of these measurement property, the mathematical operation that is possible, and the advanced operations that can be done are inclusive as we climb the order. So for nominal level measurement, apart from equal to or not equal to, is carried over to ordinal level measurement, and so any measurement at the ordinal level will have mathematical operator of equal to or not equal to, as well as greater than or less than, and so on. Basically, when two variables are measured at different levels, as a general rule, the choice of measure of association will depend upon the lowest level of measurement of the two. For example, if we are to investigate whether there is association between sex, which is a nominal level measurement, and job satisfaction, which is an ordinal level measurement, the lowest level of measurement for these two is nominal level measurement, and this will determine the measure of association that can be calculated. It is important to remember that all these measures do is detect association. They do not necessarily show the stronger relationship where one variable causes change in another. Therefore, we can say that relationship or correlation is simply association and not necessarily cause-effect relationship or prediction. Now let us look into the different level of measurements and the analysis that is applicable. So first, we can have the nominal variable. Example of such nominal level measurement variables can be gender, race, and religion, say for example. And the methods of association that is applicable can be the phi coefficient, the Kramers V, lambda, the chi-square of independence as in cross tabulation. The assumptions underlying nominal level measurement variables for their associations are: number one, the variables must be categorical. Number two, the cells should be frequencies or counts of cases. The levels or categories are mutually exclusive. Adequate sample size for each of the categories being analyzed. And finally, if a zero is present in the cross tabulation, no association can be assessed. The nominal level measurement is the lowest level that can be used from a statistic point of view. The nominal type differentiates between items or subjects based only on their names or categories, that is identification, and other qualitative classifications they belong to. At the ordinal level measurements, we can have different examples such as social class, socioeconomic status, the ranks based on marks obtained in the examination. The methods of association that are applicable are the gamma coefficient, Kendall's tau, the Spearman rank order correlation. The assumptions that is underlying ordinal level measurements associations are the two variables must be at least measured at the ordinal level, and that the scores on one variable must be monotonically related to the other variable. The ordinal type allows for rank order, by which data can be sorted, but still does not allow for relative degree of difference between them, since the number of the scale can have only a rank, meaning the appropriate measure of central tendency is the median. A percentile or quartile measure is used for measuring dispersion. Therefore, correlations are restricted to various rank order methods, and the measures of statistical significance are restricted to the non-parametric methods. At the next level, we have the scale level measurement. So measurement at the nominal and ordinal level, their relationship are usually referred to as association. So the level of measurement at the scale level comprises both interval and or ratio level measurements. Example of such variable can be intelligence test scores, personality assessment scores, the temperature, say for example in centigrade, Fahrenheit, and Kelvin. The methods of analysis of the correlation can be Pearson product moment correlation and the coefficient of determination. The assumptions underlying the scale levels of measurement are no outliers, normality, that is, the normal distribution of both the variables, linearity, the straight line relationship between the two variables, and homoscedasticity, that the data is equally distributed about the regression line. The interval type for the degree of difference between items, but not the ratio between them. All measures of relationships are collectively termed as association. The measurement at this level qualifies for the term correlation. The ratio type takes its name from the fact that measurement is the estimate of the ratio between a magnitude of a continuous quantity and a unit magnitude of the same kind. A ratio scale possesses a meaningful, unique, and non-arbitrary zero value. All statistical measures are allowed because all necessary mathematical operations are defined for the ratio scale. Let us look at the special correlation methods that are available. They are referred to as the special correlation methods because they are more or less equivalent to the product moment coefficient of correlation, which is the highest form of correlation we can have within psychological researches. That is always attempted to, and therefore each of these four methods are referred to as special correlations because they will enable analysis of the relationship between not only two variables but more than two variables. They are serving as the foundation for multivariate analysis as well. The first of the method is the phi coefficient, wherein we can have two types of variables that are more or less similar to be related. The variables needs to be discrete dichotomy or binary random variables wherein there are only two possible values under that variable. The second method is the tetrachoric correlation, wherein we can have dichotomous or even polytomous for polychoric set of data that may be derived from scale data. And the third method of special correlation is the point biserial correlation, wherein we can have two different types of variables. The first type of variable can be considered to be dichotomous binary variable with no underlying assumptions of normality, whereas the other variable can be scale variable, which is having measurement at the interval or ratio level measurement. The fourth method of spatial correlation is the biserial correlation, wherein we can have dichotomous binary variable with underlying assumptions of normality on one side and a scale level variable on the other side. So all four of these methods of spatial correlation are having outcomes which is more or less similar to the Pearson product moment coefficient of correlation, and as such they are referred to as the spatial correlation because they are assumed to be equivalent to Pearson product moment correlation. Those are the method of associations that are possible for the relationship between two variables. Now let us move on to the relationship between more than two variables. Firstly, let us look into the part or semi-partial correlation. We measure individual differences in many things, including cognitive ability, personality, interests, motives, attitudes, and so forth. Many times we want to know about the influence of one independent variable on a dependent variable. But one or more other independent variable pose an alternative explanation. In such a situation, we would like to hold some third variable constant while examining the relationship between the target variables, say for example x and y. With assignment, we can do this by design. However, with measures of individual differences, we can do this statistically rather than by manipulation. Therefore, the measures of strength and direction of the linear relationship between two continuous variables, say for example x1 and x2, whilst holding the effect of another continuous variable or variables x3, x4 and so on, constant for one of the target variable, either x or x1 or x2, is referred to as part or semi-partial correlation. The assumptions underlying the part or semi-partial correlations are more or less similar to that of product moment coefficient of correlation for each of the variables, that is, no outliers, normality, linearity, and homoscedasticity. Let us look at partial correlation, which is the measure of the strength and direction of the linear relationship between two continuous variables, say for example x1 and x2, whilst controlling the effect of another continuous variable, say for example x3, x4 and so on, constant on both the target variables such as x1 and x2. This enables us to have the influence of, say for example, two or more other variables that are continuous to be held constant for one of the target variable and see how those two target variables can be related together. That is possible with the part correlation, and in partial correlation, in the relationship between any two variables x1 and x2, we can have the control of the third variable or variables x3, x4 and so on held constant for both the target variables. This enables exploration of many of the associations between the variables possible. The assumptions underlying partial correlation, like the part or semi-partial correlation, is more or less similar to that of the Pearson product moment coefficient of correlation for all the variables and their relations. No outliers, normality, linearity, and homoscedasticity. Now let us move on to the relationship between one variable and set of other variables. This is usually analyzed employing multiple correlation. Multiple correlation is the measure of the strength and direction of the linear relationship between a continuous variable x1 and set of other continuous variables x2, x3, and so on. So it is the relationship between one single variable and a group of two or more other variables. The assumption underlying the multiple correlations are no outliers, normality, linearity, and homoscedasticity. If we look at the part or semi-partial correlation, the partial correlation, and multiple correlation, we can see that all the assumptions underlying these methods are similar to that of the product moment coefficient of correlation, which is to be fulfilled individually for each of the variables and between the variables. Finally, Pearson correlation coefficient facilitates an understanding of its generalization to multiple and partial correlation, to factor analysis, and to questions of validity. Therefore, multiple correlation partly enables evaluation of validity of psychological constructs. Finally, let us move on to the canonical correlation. Canonical correlation is the measure of the strength and direction of the linear relationship between two canonical variates that are usually referred to as latent variables. These latent variables are formed by linear combinations of two or more variables. Therefore, canonical correlation enables groups of variables that are distinctly grouped can be correlated together. As such, one group of variable, that is, one group comprised of two or more variables, and its relation with another group that is comprised of two or more other variables can be related together. Thus, canonical correlation enables the relationship between groups of two or more variables, and it is a multivariate technique with the underlying assumptions of Pearson product moment coefficient of correlation, no outliers, normality, linearity for each of the individual variables and between the variables. The canonical correlation is multivariate analysis of correlation. It is the statistical term for analyzing latent variables which are not directly observed, that represent multiple variables which are directly observed. Canonical correlation enables latent variable model based factorial validity for psychological constructs and items of psychological scales. The measures of associations, as such, do not necessarily show the strength of the relationship where one variable will cause change in another. This is done by regression, which can be considered as a separate topic. Thank you.